as well, which is a bit tricky. Right, so good afternoon, everyone. Welcome to today's Resilience of Autonomous Systems seminar. I'm really pleased to introduce our speaker today, Professor Kerstin Eder. Kerstin is a professor of computer science, and she heads the Trustworthy Systems Laboratory at the University of Bristol. And she is an internationally recognized expert who specializes in the analysis, verification, and validation of complex systems with respect to functional correctness, safety, security, performance, and energy efficiency. And her seminar today will focus on security-related resilience concerns of advanced driving systems and smart mobility services. So Kerstin, if you would like to share your screen.
Yes, thank you very much for the introduction, Radu. I shall share not this one, that one, and I shall. Okay. So can you see the university logo?
We can see the first
Wonderful.
one, yes.
Okay, welcome everyone. Let me just see whether I can. Yeah. So welcome everyone. I'm Kerstin Eder. I'm really pleased to talk to you today, and I would like to thank Radu for the opportunity to do so. I'd like to focus my seminar on an operational cyber resilience method. I'd like to introduce you to this. I have two aims or objectives for today. One is to raise awareness of the CyRES methodology, and the other one is to mobilize your curiosity to engage and contribute and to be inventive. We've only got very limited amounts of time, so let's start. CyRES is an engineering methodology for operational cyber resilience, and it is focused on the automotive sector because the existing approaches for cybersecurity in the automotive sector are not fit to deliver the resilience required for safe mass development of advanced driving features or smart mobility services or all the rest of this new development into autonomous driving. And what I would like to do is I would like to start with a resilience primer, in particular a cyber resilience primer. So a system is resilient if and only if there is justifiable and enduring confidence that it will function as expected when it is expected. Resilient systems in particular can recover to a functioning state following a disruption which has already changed the system state, so which has affected the system. And a system is secure if it displays this property in the face of an adversary, and it is cyber secure if it does this with an adversary that is not co-located. Okay, but sometimes we don't even need to go that far. But let's take this as the ground from which we shall start. Now, let me introduce you to the problem. What we had before was a system with a bounded scope, clear system ownership, known interactions of the system within the system components, predictable function, and benign intent. On the right-hand side, you see the engineering V that is typically employed in the construction, in particular, the development of systems such as cars. You've got system engineering, management plan, the requirements, definition and decomposition all the way down. And then on the right-hand side, you see the corresponding verification and validation steps all the way up towards system deployment. And this has served us really well for bounded, fully known systems where we have enough time to go through this process. And in fact, the engineering V is used to optimize the design to known operating conditions. What we are faced with now is quite different. and it's a consequence of vehicles being connected and a degree of autonomy in the system. We've got systems with unbounded scope and often unknown system boundaries. The ownership question is not entirely clear. Interruptions are unknown, especially if you consider the system to consist of several vehicles, not just one. You get emergent behavior and malicious intent. Now, there is a problem with the classical V&V in the sense that the traditional V&V techniques are less and less effective in achieving what we need and what we expect to see from vehicles. And in many cases, they are even counterproductive. So for the automotive and transport systems that are being developed, engineers are unable to deliver convincingly executed V&V that meets the standards. And if we were to adopt the classical V&V model to meet the challenges that I've just outlined, then we face exponential complexity. Because at design time, the parameters and variables will be unbound, especially if we consider unbounded systems with no known bounds. And the analysis would then need to be performed over an entire range, and that's computationally infeasible and results in state explosion. So that's not really viable. And for these reasons, classical V&V is not suitable to develop computationally scalable techniques to prove that there is sufficient confidence in the implementation of each one of the elements, the system's overall behavior, and in particular looking throughout its entire lifetime. And it is also not possible to demonstrate and collect the evidence that the system behavior satisfies the defined functional and operational cybersecurity and safety requirements using the traditional approach. So the engineering V cannot accommodate all the operating conditions of these new systems, and we are faced with a situation where we have to change. Let me illustrate this on a very simple example: braking. Right, so everyone knows how important brakes are in a car. They're almost the most important. Cars these days have enormous attack surfaces, right? So you look at vehicle-to-vehicle communication, you've got engine control, you've got transmission control, you've got all the telematics, you've got access through keys, anti-theft, you've got the onboard diagnostics, which can be quite problematic. And then there's all the entertainment and navigation. And we want to focus on the ABS system. Now, braking used to be quite simple. And traditionally, ASIL-D is used as a design rationale associated with braking. And that is still the case. And ASIL-D is the highest classification of initial hazard, which is defined in a standard called ISO 26262. And that represents likely potential for severely life-threatening or fatal injury in the event of a problem. And that implies simplicity of design, a certain level of replication, and 0 to a small number of lines of code in order to meet ASIL-D. Now, braking is or used to be simple for fluid-based electromechanical systems where this all applies, but braking has become digital and hence quite complicated. So the braking systems have evolved to include ABS, which works at all sorts of different speeds with individual wheel braking, acceleration and steering. There are various sensors, which may or may not be augmented by machine learning. You have data fusion, algorithmic arbitration in order to optimize the system. And all this is connected over a shared network infrastructure, which we will have a look at later on. So we're getting quite a number of sensors and in the order of millions of lines of code, not including training data sets. That you can already see is no longer simple. And because of all the software and the IT infrastructure between the wheels and the place where you exercise the control, we can really say there is no direct connection between the control and what's happening on the physical side of the machine. And that clearly undermines our ASIL-D assumption. There have actually been successful cyber attacks against braking systems based on various vulnerabilities. For instance, contradictions that may arise in a data stream, denial of service attacks, non-determinism, because there is arbitration between complex algorithms and there is typically no ground truth. And a particularly vulnerable place is also where analog signals are translated into digital ones. And I want to focus in particular on those. It was actually surprisingly simple to find a paper to tell you exactly how to do it. I just said attack ABS, and up came this paper with an exact how-to list. It tells you exactly how to do it, right? You place an electromagnetic actuator in the air gap between the ABS sensor and the ABS tone wheel, right? So this is an attack where you have to have physical access to the car, and it shows you exactly how to do this, how to place this electromagnetic actuator, and that results in two opportunities for attack. A very simple disruptive attack so that you confuse the ABS sensor, and that is by simply placing this actuator next to the module that comes from the car, and that means you're superimposing a malicious magnetic field on the original one, which confuses the ABS sensor. But if you want to properly take control, you take a shield, you block out the original, and then you can fully confuse and deceive the ABS sensor, and all sorts of bad things can happen. I was shocked how easy it is, and this has been known and published since 2013, so quite a long while. We wanted to see whether it's possible to do this without actually having to access the car. And in order to do this, we had a close look at the communication infrastructure, and that is typically the CAN bus. So that's the most used in-vehicle network protocol, which supports the exchange of data between the ECUs, the electronic control units in the car. And you can see the overall communication infrastructure. You've got sensors, you've got telematics and infotainment, and then you've got the different ECUs from different domains, and they're all going into a gateway, and that is connected to a quite problematic onboard diagnostics unit, which you have to have, but has also been abused for various different attacks, because that is where you can interact with the car. And what we have done is we have looked in particular at the CAN bus, because the CAN bus has traditionally been used in cars for decades, and it was originally designed to be used in a closed system. So it lacks security mechanisms by design, and is therefore quite vulnerable to various attacks and utterly unsuitable for the sort of systems we are looking at now, where we have clearly got or no longer got a closed system. What we have done is we've replicated what you would find on a car on a board. So we've got the network together with the motor control. You can see the input controller, the motor controller. You can see the motor on the left-hand side, picture in the right corner. And on the right-hand side, in the right picture, we can see the full CAN bus infrastructure, including wheel control boards for each wheel, right? So right front, right rear, left front, okay? And so you've got the entire infrastructure. And last year we had an MSc project which had the challenge of successfully implementing attacks on this left-hand side board. And this was an MSc student who came from a completely different discipline, no engineering discipline, who did our conversion course, which has not focused on embedded systems, but instead on computer architecture and programming and software development. And Anna was able to successfully launch a denial of service attack based on a UDP packet flood, which used a broadcast destination IP. By injecting less than 50 packets in quick succession, it was possible to crash the application layer of the input controller. After a while, the motor controller also stopped sending requests and the entire system ground to a halt. And it only was possible to resurrect it again after a full restart. Now, we did this in lab conditions, and it was not possible to communicate with this wirelessly. And for good reason, right? You do not want this to escape. And this year we'll take this a little bit further. What we have done with Anna is to use this experience and develop educational material for secondary schools so that kids in the school can learn how easy it is to launch a cyber attack on a physical system, with the hope of raising engineers that are aware of the problems and do a better job than what we have done so far. So let me focus on operational cyber resilience then. The CyRES methodology is a new engineering method that goes beyond the traditional V that we have previously used, and that already I said is no longer suitable for the sort of systems we are considering. In the CyRES methodology, we are considering the design stage as well as the operational stage. So as long as the system is under the design stage, we develop it, and in addition to this though, we are making sure that we have adequate monitoring in place in order to detect when things go wrong. We seek to understand what has gone wrong using simulation at real time. And we then need to react and plan to this in order to mitigate, contain, and recover. And so with CyRES comes the design time considerations, but in addition comes a runtime environment that supports exactly this detection, understanding, and reacting during operation or at runtime. There are three principles that underlie this methodology. The first one is to increase the probability of detection, understanding, and action. The second one is to increase the number of engineered differences in the system. And the third one is invoking a continuum of proactive updates. And I'll focus on the first two today. And the methodology, the CyRES methodology, achieves these by building engineered differences into the instances of the deployed systems during the design stage. So this is an intellectual challenge, and I'll show you a very simple example of how this can be achieved. Then there's a rapid cycle of detection, predictive modeling, and simulation, which results in updates to the deployed systems during operation. And hopefully this means we can recover before catastrophe hits. Now, the certification arguments are then centered around 6 parameters. The first one is the probability of detecting threats, PD. The second one is the probability of understanding threats, PU. The third is the rate of deploying mitigating actions, RA. The fourth one is the time for a threat to propagate. That's TC. So that's the time of the catastrophe, effectively. And the fifth one is the quantity of engineered differences, N, in the system. And the final one, the sixth one, is the frequency of proactive updates, F. And our cyber resilience then becomes a function over these parameters. So overall, the method is an operational methodology because it includes the operational as well as the design stage. And we believe this is standardizable. The method itself is capable of being tested in court or by publicly appointed regulators, Operators understand what evidence should be produced by it and are able to measure the quality of that evidence. And the evidence itself, the evidence produced, is capable of being tested in court or by publicly appointed regulators. Now, the goal of the ResilienceKerstin project was to assess economical and technological feasibility of this methodology. So is it economically viable? And how long does it take for this to be implemented? And it is interesting to see that it is economically viable, and actually the technology is at a stage where in many places it doesn't take long for it or much for it to be implemented. And we've got various demonstrators to show this. Now, there are mathematical foundations for the analysis of these systems. I want to focus in particular on a performance metric, PT. The performance metric is used to capture critical functionality of a system. And you can see in this graph, on the y-axis, we have the performance ranging from 0 to 1, where PT of 1 means the system is fully functioning, and PT of 0, PT equals 0, is the system is not functioning at all. So this is here at the bottom. On the x-axis, you've got time, right? So at the bottom, nothing works at all. At the top, everything works fantastically. Okay. Now we have a network of n individual vehicles, and each one of them has, for each one of them, we can determine its performance. And we can calculate the average performance for all vehicles. So that gives us the overall performance using this summation and equation. We can use the performance metric to determine the resilience during an incident event E, which has a start and an end. So the start is at time t equals 0. That's the performance of at least one of the vehicles being below 1. And the end of such an incident is when the overall performance of the system is equal to 1 again. So that's for all vehicles. This helps us to define the time to failure, which is the length of time between the start of the incident and the first time it decreases below the minimum functionality threshold. Now, this minimum functionality threshold is indicated here. You've got minimum functionality threshold with a dashed line, and here we're dipping below this. So that's the time to failure. And then we can also define a time to recovery. That's the time until the performance returns to an acceptable level, right? So we're getting out maybe with an initial response to the event. And then, of course, we've got more time until full recovery has been achieved. Now, if we look at this timeline, the incident lasts from t equals 0 to an endpoint, capital T. Then, in a very simplistic way, we can identify 3 phases: the time to detect the incident, the time to understand what's going on, and the time to respond to it. So if we now introduce the point of the catastrophic event happening as TC, which we've previously seen in the equation where I had the 6 parameters, then the point of catastrophe can be defined as a point where it's no longer maybe financially viable to fix the problem, or the performance of the overall system is below the minimum functionality threshold for a specified amount of time. And for very small incidents, perhaps the catastrophe will never happen, right? There are very small incidents that we can live with, and they'll be ironed out next time we bring the vehicle to an MOT or so. So to avoid the catastrophe, we need to complete a response before TC occurs. So for complete cyber resilience, we need the end of the event. Yeah, up here we have the event T, or time T equals capital T. We need that capital T, the end of the event, to happen before the catastrophe hits TC. Now, if the catastrophe hits before the window of detection, then we failed to detect. If it hits before the end of the understanding, then we haven't understood. And there is, of course, also the possibility that we have understood what's going on, but we weren't fast enough to develop and then apply a fix for the problem. So we didn't actually get up out of the dip in that curve before the catastrophe hit. Now, what we want to do is we want to avoid catastrophe. And the challenge is to reduce the probability that a random event leads to catastrophe to a level which can jointly be covered by insurance and acceptance of a certain amount of risk. Now, to achieve this, we have two options. We reduce T, which is our priority A in this graph here. On the x-axis on this graph, you've got the probability of catastrophe. And on the y-axis of this graph, you've got the number of units in the system. And reducing T means the duration of the event is reduced. So we are bringing the end of the event forward, away from the point at which catastrophe might happen. And that means we need to detect, understand, and respond quicker. The other option is to increase P of T during the event, and that's our priority B. Now, remember, P of T is averaged over all vehicles. So improving performance of some will improve the overall performance of the system and thereby help us increasing P of T during the event. So in the diagram, if we look at this diagram, we can see the two priorities. They partition the space of all events, and we can also see how they affect, how they impact on safe and unsafe units in my system. So the area shaded in red represents the loss from events which leads to catastrophe, and it's our aim to reduce that, so that catastrophic loss here in this area. Now, informally, the remaining white area represents the resilience of the system, consisting of the number of units which are not affected by an event and events which do not actually lead to a catastrophe. Well, how can we do this? How can we achieve this for both of these options? Let's focus on the first one, detecting, understanding, and responding quicker. This means reducing T, so bringing the end of the event forwards. Now, if I treat the cyber attack as if it was a system adaptation, then you can easily make a link to something this community should be very familiar with. This matches the vision of autonomic computing, which has been promoted by IBM well over a decade ago, almost 2 decades ago, in 2003, where they introduced autonomic computing, which means computing systems that can manage themselves. And this is based on an autonomic element, which typically consists of one or more managed elements. So the element that is managed here would be the car. And then above that, you've got this operational system. And we know this as the MAPE-K loop, where you have monitor, analyze, plan, and execute. And IBM introduced that then in order to be able to dynamically manage systems which are acting within a larger system. And in fact, there has been a fantastic seminar in this series about self-adaptive systems. And Dunning has introduced this with the same sort of enthusiasm and we're basing our research on this paradigm in the self-adaptive systems community. So this community is really ideally suited to contribute here. And this is only like 2 or 3 seminars ago, which is really useful for me, because if you want to know anything more about this, I refer you to Danny's seminar. Now, since then, we've done a lot about modeling at runtime, and I think modeling at runtime is critical for the CyRES methodology. But modeling at runtime has already been applied to the traditional MAPE-K loop. So you've got your monitor, your analyzer, your planner, your executive, and you have this all referring to models at runtime. And we expect to need these models as a very important column on the right-hand side of our CyRES methodology, where we have the operational system, which takes reference to models at the different levels of detecting, understanding, and acting. Now, if we look at the MAPE-K loop, then it's really simple to identify where we can transfer it, right? This is our detection, this is our understanding, and this is our reaction. And it's really important that this community realizes how much the advances that the community has made over the years would be applicable to this methodology, and how much we need the expertise in this community in order to drive this forward. Roughly speaking, because we don't have enough time here, our detection is done using monitoring. So monitoring at runtime, real-time monitors, and there is interesting monitoring going on at different levels in the system stack. So you can now equip chips. There is enough silicon available to do on-chip monitoring of all sorts of things. And there are interesting technologies and companies. So there is Mortec, and there is also Ultrasoc. Both are developing systems that allow us to monitor the hardware, and that information can be projected upwards in the system stack, and we can make use of that as part of the monitoring. And of course, you can also do behavioral monitoring in the software layers. So this applies throughout the entire system stack. The understanding we do through real-time simulation. And that means simulation techniques are severely challenged to provide input in real time. So we need to be selective about what we can simulate on board and what we want to delegate into the cloud. It is pretty useful to be able to understand whether an attack means you ought to stop right now, or whether it's one of those which you can mention next time you bring your vehicle to the MOT. And being able to tell the difference in real time rather quickly is key to preventing catastrophe here, which is why simulation is extremely critical in order to provide us this first understanding of what's going on and what the impact of the observed change of behavior is on the operational status of the system. And then, of course, we need to react. We need to react, and that means we are deploying, we are devising and deploying fixes, mitigations, containments in order to get out of this performance dip back into system functionality, at least above the minimum functionality threshold, but really we want to go right above to where we came from, namely the performance at level 1. Okay, so we've looked at detecting, understanding, and responding quicker. The other one I want to look at is increasing P of D during the event. And that's a really interesting challenge. And it gets me to the principle of engineered significant difference. It's a really interesting principle, and it's really necessary, because in electromechanical systems, each system and platform is different, and consequently, each would be expected to be susceptible to failure in a different way, and in particular, at a different time. So, therefore, the harm that might arise from failure occurs with statistical probability, one device at a time. And it is this principle that forms the basis of standard safety calculations. Now, in digital system, it is possible that a fault that has been identified could manifest itself in all digitally identical systems, and worse, that could happen at the same time. And that can give rise to a global catastrophic failure at the level of the entire system rather than individual vehicles. And that would include police cars, ambulances, and fire engines. That would mean the infrastructure that we typically rely on when things don't go well. So why significant difference? Now, in biology, survival of a species is often based on diversity that is arising from heterogeneity. So we need to move away from digitally identical systems to systems with engineered significant difference through the deliberate introduction of differences that are not detectable by the user or operator. So they are effectively equivalence classes in terms of the overall functionality of the system, but they may help prevent cyber attacks that would otherwise affect all systems because systems are individually different. In the best case, if we do this well, then such a cyber-physical system has entries which are very different from each other, and they would then fail, and if they fail, they'll be subject to calculation of harm in the same way as the electromechanical systems, because they are all individually different, and therefore they would all individually be affected by the cyber attack in slightly different ways, possibly not at all, and in particular at different times. So that's the whole idea behind significant difference. Here is a very simple example of how this can be achieved. It's focused on differential power attacks. These are side channel attacks which rely on the correlation of data from repeated runs. So you repeatedly run a cryptographic algorithm, and you are relying on the same instructions being executed. And here you can see a DPA attack on DES, and you can see at the bottom here, in the side channel attacks, the correlation allows the secret to be revealed, so the attacker can guess to the correct subkey because it's possible to see in the power trace. Okay, and that's not good news. Now, what can we do about this? We can introduce diversity. We can introduce diversity in the execution. And that removes the correlation between the different runs, which this type of attack relies on. And we can achieve this by randomizing instructions during compilation or during execution, or both. And what we're doing is exploiting available instruction level parallelism, not to increase performance, which is typically aimed at by computer architects, but to increase non-determinism when instructions don't have any dependencies between each other. So if we look at this example here, we've got an add and an XOR, and we've got a single pipeline processor. Then for this instruction sequence, we have the add executed before the XOR. Notice there's no register dependencies, so no data dependencies between the two instructions. If you have a processor with two pipelines, you would execute both of these instructions possibly in parallel, one on the integer unit, the other one on the logic unit. Now, in non-deterministic computing, you would either choose to do the add or the XOR, and then you would do the other one. Okay, and you would do this randomly. You would choose to do this randomly. And so this is really very simple, and we are exploiting something that's already been exploited to increase the performance of a computation. But in this case, we are exploiting it to increase cyber resilience. So this is a very old concept from 20 years ago that was introduced. This is a processor called non-deterministic instruction stream computer. And it relies on randomly issuing of instructions. And these employing this random issuing results for this simple example here in 4 different execution traces. Again, we've got 2 adds, 2 XORs. There is no dependency between these instructions, and so I can execute them in any order. In addition to this, what we can do is we can apply functionality preserving sequences. So we can resequence code. So for instance, on the left-hand side here, we've got a load, an add, and a store, followed by a load, an add, and a store, but we're using different registers. Okay, so these 2 are completely independent, but if I resequence them and put the loads together, the adds together, and the stores together, then I increase the number of execution paths to 13. And that gives me a much broader variety of power traces to observe than if I was to execute it just like this. Now, if we look at this, by randomizing the instruction stream, the non-deterministic processor, which was called NDISC, has achieved an interesting change in the DPA attack on this. We have very simple additions and modifications to code generation and execution, and that can be implemented in either the compiler or the hardware. And so if you run exactly the same attack, then you get something like this. And so where we previously saw the spikes, they are still there, but the noise we've created through the randomization removes the opportunity for the attacker to exploit the fact that the same instructions are always executed, and thereby introduces obfuscation that is sufficient to no longer clearly identify where the subkey was hidden and where you guess the correct data in order to find the subkey. Now, this is something that can really easily be employed, and it doesn't cost anything, so it's readily available. So when we assessed the technological feasibility of introducing diversity into the execution stream, in principle, this is off the shelf. The research has been done 20 years ago. This could very quickly be employed in any processor, and compilers also would be capable of doing this. It gives us interesting verification challenges, because we need to make sure that what we're doing does not change and alter the functionality, which is not what we are intending. We're just intending to alter the observable power consumption of the device. So for verification, this is a challenge, but for cyber resilience, this is a gain that we could easily implement, and that is in principle ready to take off the shelf and get going. Now, significant difference has challenges because it has been deemed economically infeasible on other fronts. And that is because the need for V&V and product certification could not in the past be borne on a per unit basis. So you can't do individual V&V for each and every instance of a system, right? The entire infrastructure relies on us doing it once and then making lots of them. So we need to think about how much digital identity we actually need in our system in order to achieve the verification we desire. And in addition to this, of course, chip design and manufacturing is a very tough place to be. And the ecosystem, together with the fabs and the tool chain, favor what is called a volume industry, in which when you're not number 1 or 2, you're basically not in the game. That's quite tough. And it's also been found extremely challenging to determine that one system or component is indeed significantly different from another one. So for engineering of significant difference to be a viable technique beyond compilers and execution streams, it must be possible to address each of these points. But that's an intellectual challenge, right? As a community, we should rise to this challenge and we should look into where we can change things. This requires a change of mindset to spot equivalence classes and to design systems differently. Okay, so then I promised to introduce you to this methodology. And the other goal that I set out to do was to mobilize your curiosity, to get engaged and to apply your knowledge and your expertise and all the good things that have come out of the adaptive systems community. And Radu tells me that the adaptive systems community is part of this seminar series. So I'm hoping that some people might feel addressed by this. Okay, so where are the opportunities? So this CyRES methodology challenges the way we design, engineer, and operate systems. Engineering differences into systems is really an interesting concept. It asks the question, how much digital identity do we really need in order to get what we need and what we want from the system? So, you know, the non-determinism or introducing non-determinism into an execution stream is based on the observation that there is typically a large number of valid changes of processor state in order to achieve a particular computation and to implement an algorithm. Can this principle be transferred into other areas of computer science, computer engineering, electronics, materials? Can we identify the equivalence classes that we need in order to achieve this? And can we exploit them to make systems more resilient? And then, of course, there's the detection, understanding, and acting. The challenge of monitoring. What do we monitor? When do we monitor? What's the overhead? And how do we label things so that we can take advantage of them? Because if you look at this right-hand side here, this is the knowledge base that we're using at runtime. These are our models at runtime to feed new information into and to get information about what is known, what are the scenarios, what's the guidance in terms of mitigation and recovery. We need runtime VNV, so we need to shift verification to at runtime. And we also need simulation at scale, and that requires intelligent test generation at design time, but potentially also live at runtime, and also efficient techniques for test selection, because at runtime, every second counts. So just running the entire test suite might not be a good idea. You might want to order your tests in such a way that the ones that reveal the answer to the question you're asking are being run first. So there are lots and lots of intellectual challenges. And I hope that some of you perhaps might find this interesting and might want to work with us to make this a reality. Okay, so this brings me to the end of my presentation. Thank you very much for the opportunity. And I should say that the material that I have presented is the result of a project, a funded project by Innovate UK in collaboration with CCUF, a project called ResilienceKerstin. And the CyRES methodology itself and the material that I presented is joint research with a number of people that have worked on the ResilienceKerstin project. Thank you.
Thank you very much, Kerstin, for a most insightful seminar. Very exciting directions that you proposed here, and I'm sure there will be questions about some of these. So if people do have questions, please do ask them. Ian, you had a question in the chat, or would you like to pose that question yourself? So there is a question on the chat asking whether the use of runtime monitoring does not introduce new attack surfaces.
It very likely will. So it very likely will. If you think about Trojans, which can go onto the chip, you know, I'm talking about on-chip monitoring. and the fantastic opportunities it provides. But of course, if you don't own the FAB, you never know what else is, who else is listening, and where the information is going to. So we will have to be resilient on that front as well. We have to be changing the way we design these systems right from the start. And the same applies to the runtime monitors. Although I cannot see how we can survive this without runtime monitors. And that brings me to the problem of there not being any ground truth, right? Even with runtime monitoring, it's very difficult to establish the ground truth.
Indeed. Colin, you wanted to ask a question?
Thanks, Kerstin. Very interesting stuff. You had a graph earlier on where you showed a performance graph dipping below a threshold. Two thoughts came to my mind, really. One was that you presented it with this value of 1, meaning everything was perfect.
Mm-hmm.
And I wondered what your thoughts were about there being a potential a threshold which is good enough. And I wondered on the other end, where we had a failure, whether it was okay to just have one level of failure. And again, whether we had in very complex systems, the fact that we might dip into areas of concern but not failure. And I wondered how that might change the way we thought about performance.
Yeah, absolutely. I think these are interesting observations to make. You know, here is the minimum functionality threshold, which I guess is what you would mean with good enough. You know, this is the minimum. Maybe there would be something above this that says ideal or so. You know, or well, ideal is one, but you know, good enough maybe somewhere in between the minimum, the bare minimum, and the, you know, good enough. Yeah, I mean, you know, this is a rough idea on formalizing the problem, and I don't see a reason why we can't extend this to different modes, etc.
Yeah. What I was thinking, as much as anything else, is there are I can see them very much informing the types of adaptation which are allowed. Because if we have a threshold that means this is, you know, we're approaching the point where people die, this is quite different to saying we're approaching a point where people are going to be inconvenienced.
That's right. That's right. So what part of the methodology, and there is a large report available on this, which I can get to you if you would like me to,
Mm-hmm.
is relying on almost like an onion type shell, where we're saying, okay, where are we? How far away from where we should be are we?
Mm-hmm.
And that governs the mitigation and the need for action. And so if you, it's almost like a matryoshka or an onion that you can imagine. And it's important to determine, actually, when you find yourself outside the area that you've designed for, it's important to determine how far outside. So where in that shell of an onion are you? And therefore that will determine as to what you should be doing to get back.
Yeah, and I think that when you talked about engineering difference, you know, this idea of knowing distance measures in all kinds of contexts is incredibly hard. I don't, you know, I wish I had some magic wand on those. I don't. It's things that are going around my head too at the moment.
It is very, very hard. It's an intellectual challenge, but you can see I try to motivate where that comes from, right? And by saying, you know, these are the options we have in order to minimize the little red area in the graph at the bottom right corner, where we have a catastrophic loss. And these are the only instruments we have in order to avoid this. And so yeah, there are intellectual challenges, but that's what we're here for, right?
Yeah, absolutely. Wouldn't be fun otherwise.
So one other thing I wanted to ask Kerstin, as you went through the presentation, I kept thinking, well, what aspects are actually security specific, because the methodology seems to be more generic. So perhaps other types of disruptions could equally be treated in this manner.
So the methodology has specifically been developed for cybersecurity, but you can see this is generically more applicable. And so I think it's fair to say that this can be transferred.
Yeah, I would imagine so. So good. Yeah. Well, one other thing I wanted to ask in particular with this very important parameter that you introduced, this catastrophe threshold, I guess, TC. It makes a lot of sense mathematically, but I was struggling a little to come up quickly with examples of where catastrophe would happen after a period of time, especially because you mentioned the break. So I would imagine that there isn't much time at all, if any, to recover if the brakes are broken, as you put it.
Yes, well, it depends. You see, if it's the normal brakes or the ABS, how often do you actually slam your foot down on the ABS? When the ABS kicks in, right? You get this grinding sound of the ABS coming on. We focused on the ABS in particular, but yes, indeed, there is typically not much time, and that's a real problem. Especially when it's affecting the components of the vehicle that are safety critical, the steering, the acceleration, and the brakes.
Oh, this is a very good example with the ABS. It might not be needed for long periods of time, but it also makes me think it's hard to estimate that TC parameter because you won't necessarily know when you'll next need the ABS.
Yeah, this is hard. And in particular, I mean, if you look at the existing cyber attacks, often they are not detected for a very long time.
That's true, indeed. Yes, the intrusion might be ongoing for a long period of time.
The nature of the beast, right?
Yes.
that it remains undetected for far too long.
Yeah. I also keep thinking, well, what other safety implications that this engineering of differences might introduce. I'm aware that in many cases there are race conditions that are not identified through testing, maybe even verification of a formal nature, and the system still operates fine because the race conditions are sort of benign, shall I say. But if these differences in ordering of operations are introduced, that those race conditions might lead to failures.
Yes, they might occur more. Those might occur more frequently if you change parts of the system that previously were stable.
Yeah, so I suppose I guess that the approach would work fine, but it comes with a number of assumptions as well, such that perhaps such problems don't exist.
I agree. It causes a verification problem, a challenge.
Yeah. Right. Any further questions for Kerstin or comments?
So as you were talking there, I wondered if there was, with the TC, there's an interplay of components, because we very much talked about a failure here, but I can imagine a system in which we have sensor failure, which leads to a change in TC. So you said, for example, that the ABS, if we detect ABS going off, then a sensor, so imagine a distance sensor for automated braking, suddenly becomes that a lot more sensitive to failure. So we might be able to brake in TC time if the ABS is working to avoid a crash. But if we detect the ABS is not working, TC changes to a different value because we've got a less responsive system, and therefore we're more reliant on the sensor accuracy being correct for us. So there's an interplay there between the systems, and I think we know these are complex, but I can imagine that your adaptation is a function of the knowledge you have in this evolving system. So I think I can see that parameter changing over time and affecting our adaptation.
Yeah, potentially there's no guarantee that the time to catastrophic failure is always the same, right? The attacker learns as well, and they can be quite persistent, and they've got time on their side. Basically, the interesting thing about these systems is that in comparison to the electromechanical system, in the context of these systems, let me just go back to a slide. That one there. The attack only needs to succeed once, right? Because all systems are the same. Only the first attack takes time and expertise, and then the rest comes for free because everything is identical.
Yeah, I guess on the plus side, one can argue that there is more opportunity to modify a software component by reorganizing the statements, the operations as you described, Kerstin. Whereas if you have a problem in the hardware, like a chip was manufactured in millions and sold, that there's no possibility of fixing that. So I think we need to think about the opportunity as well.
Yes, of course, absolutely. It affects both hardware and software design, but fixes are notoriously bad. Impossible for hardware once it's solid. So you know that'll have to be firmware.
All right, I don't want to monopolize this, but I do have one other question. So as you're going through the presentation, I noticed that this requirement that you stated that you wanted the differences engineered into components to be not detectable. I was wondering if you meant that the nature of the differences should not be detectable, or the presence even should not be detectable, and why?
Well, the real idea of these engineered differences is that they kind of mimic the differences that you have in traditional manufactured systems, where they're all the same, but they're not the same because the materials are slightly different. The electromechanical systems, they are diverse, although they are within tolerance the same. Yeah. And so what I'm saying is, within tolerance, they are the same, so they're effectively indistinguishable for the end user. But with respect to their side channel properties in the case of the DPA attack and the non-deterministic execution, they prevent that through that diversity. So they're actually, through that engineering difference, more resilient, although that difference is not noticeable in the performance of the execution of the program.
Right, so by distinguishable, you meant to the user, not necessarily to the attacker. Yeah. Because I'm thinking the attacker could actually...
User, it's within tolerance, it's all the same.
Yeah, but maybe the attacker would actually be deterred if they knew such differences were introduced. Like,
absolutely, that's the whole idea. I make it really difficult. I make it really difficult for them because the moment, a differential power analysis attack relies on the same instructions being executed over and over again. So if you guess the key, then you'll get correlation that you can detect with an oscilloscope.
Sure.
But if that fundamental basis on which this attack relies, which is that the execution goes through the same instructions all the time, so when there is a spike, it's actually the data because the instructions are all the same.
Mm-hmm.
Yeah?
Now,
then,
what I was...
Then I can basically make it very difficult by removing that assumption of the attack.
Mm. I guess what I was suggesting as well is that maybe the product should be stamped with a big note warning, this product is protected through engineering differences that are randomly picked. maybe that'll deter the attacks, because as you said, there is a significant intellectual effort to break the system the first time. So
yeah,
if criminals were to know that they won't gain much benefit from putting a lot of effort into it, they won't even try.
yeah, yeah. That would be nice. That would be nice. If we could achieve that to the extent that people wouldn't even try, because it's, you know, it makes it very, very hard, not worthwhile, basically. But then the nature of the attacker is that they will attack you on a different place where you haven't yet water tightened all the nooks and crannies, right? So.
True. But you did say that the breaks are very important, right?
There's a question on the chat that maybe feeds into that, the idea of context.
Tim, would you like to ask your question?
It goes into the question really of, came up a couple of times, both the trying to assess how long you've got and also whether you should stop. My own experience of ABS is it wasn't something that was available when I was brought up, but it's obviously considerably more use on ice than it is on dry tarmac, and considerably more critical. You can drive effectively without it in many cases if you're on dry roads, but it's also considerably more help in heavy traffic. So in making the decisions as to whether you should stop or not, you start to think, well, what's the context here? Now, we make those decisions quite quickly, but my first experience of a degree of autonomy was an autonomous clutch system, an automatic clutch system. And that used to respond quite frequently to sensor errors by just stopping or just degrading the system. And in many cases, or at least in some cases, set up quite unsafe conditions with its recovery mechanisms. And so you start to see this whole problem of trying to work out your context, in the Jungian sense, and the distance metrics, as actually being a highly variable and dynamic problem. That, in one's context, you could be quite close to disaster, and in another context, you might be quite a long way from it with exactly the same system behavior. Is that one of the challenges you're actually up against here in trying to build resilience into the system?
Yes, it is. Nicely explained. That is one of the challenges. However, one of the reasons why we're shifting this sort of analysis to at runtime is because it is impossible to do this at design time, right?
Yes, I quite agree. Yeah.
All the possible situations in its lifetime the car might encounter. This is not feasible, which is why we're shifting it to at runtime, and the monitoring monitors a single instance. It doesn't monitor, the onboard monitoring monitors a single instance. So it knows exactly where the car is, what day it is, it has all the contextual information. It can use that information at runtime to make a decision. And what it decides for that vehicle might be completely different to what the same system decides under different circumstances for a different system.
Yes.
Which is the benefit of doing it for a single instance at runtime.
Yes. Yes, and you also, we could go on forever, but in the example, and it was a great presentation, by the way, it's really thought-provoking. I really mean that. In the context of what you were just talking about, is saying, well, we know position's usually one of the things that you really struggle with knowing well. In my experience of other systems, it comes with all sorts of errors and risks. Is that actually something else that's actually quite hard to bring into the context?
Yes, it is. Effectively, there is no, this I capture with, there isn't a ground truth.
Yes.
The lack of ground truth is a real problem.
Yes, yeah, I can believe that.
And there is no remedy for this that is an obvious remedy. It's all moving targets.
Yes.
And that makes it very, very difficult.
Yeah, and trying to segment the problem so that how you choose what you do fast and what you compute slow on real time in the system.
Yeah.
Yeah. Yeah, no, it's interesting. Yeah, yes, because some aircraft have different software, don't they, for each of the independent computers?
Yeah.
But you're going way beyond that type of model, aren't you?
Yes. So this is. I'm not a software engineer for aircraft, so I'm not entirely familiar with how the problem is solved in that domain. But I know that the safety standards are considerably more stringent for that domain than the automotive domain as such. But it's clear that the challenges once we go and connect systems are multiplied and much bigger than what we've seen before.
Yeah, no, thanks. I'm not an expert in any of them, so appreciate. Thanks very much.
You're welcome.
Right. Any final comment or question for Kerstin? If not, I would like to thank her again for giving this insightful seminar, and also to thank everyone who attended, asked questions, and participated in the discussion. So I'm looking forward to seeing you again at our next seminar in 2 weeks' time. And stay safe and goodbye now.
Thank you.
Thank you.
Thank you, Kerstin.
Bye.